So say we wanted to determine this integral here. Say we wanted to solve this. What method would you use? You may think you could try u substitution, but if you try it, nothing really cancels out. Integration by parts isn't really going to help you out. It's not a basic rule. So what would you do? Well, it turns out, in this case, we can use partial fractions to simplify this into an basic integrals that we know the tools for. So it's partial fractions is used similarly to u sub or integration by parts in that you're just taking a complicated function and you're trying to break it down and simplify it into functions, into one of the basic functions that you know the integral of. So partial fraction is defined as a rational function, or it's used for rational functions where you have p of x on the top over q of x on the bottom. So a function of x on the top, function of x on the bottom. And a proper rational function are the ones that we use partial fractions for, are the ones where q of x is higher order than p of x. That means the denominator is a higher order than the numerator. So we can solve integrals like that shown below. In this case, we have the order of the denominator is higher than the order of the numerator. We cannot solve integrals like this where that order of the numerator is higher than the order of the denominator. So we can do ones like this with partial fractions. We can't solve integrals like this with partial fractions. So let's go ahead and try and solve this top integral. All right, so let's start off with the example we just had, the integral of 9x plus 1 over 2x squared minus 5x minus 3 dx. But before we start working on this one, let's just kind of get a bigger picture of what the idea of partial fractions is and what we're doing here. So imagine we have this fractions 1/2 plus 1/3. My daughter's adding fractions now. I've been helping out with it a little bit. And of course, we all know what we do here is we just multiply to get a common denominator on both sides. So we'll multiply the left part by 3, the right part by 2, and we get 3/6 plus 2/6, which is equal to 5/6. So what we do with partial fractions is we're kind of working backwards. We're taking we're starting with the 5/6 and working backwards to the 1/2 plus 1/3, because that helps us get our function into two functions that we can integrate. So we take our function and just take it out of the integral for now, and just so we can work with it a bit before we put it back into the integral. And now we can factor out that denominator, just kind of like the reverse process of how we distributed the to make the denominator 6 in that simple fraction above. This time we're going to factor that out to get two terms on the bottom, like the 2 and 3 up top. So now we get 2x plus 1 times x minus 3 on the denominator. And here's our big step here, is now we're just going to separate that out into two different fractions where we have the 2x plus 1 on the denominator 1 plus b over x minus 3 as the denominator in the other one, just like that 5/6 could be separated out into something over 2 and something over 3. And this is sort of the big step with partial fractions, is making this leap. But you can see we're just sort of undoing a process that we're all familiar with. So it's not that shouldn't be that crazy of a leap. But from here we can work on solving for a and b to make this equality hold. So what we can do is take this equality that we found up here and multiply both sides by the denominator that's on the left side. So if you multiply both sides by that, you get this big equation here. It's not as complicated as it looks, and you can see that the denominator on the left side will cancel out because we multiply by it, and that's going to cancel out the term on the bottom on the right as well. So we'll cancel out that 2x plus 1 term, and we'll also cancel out this x minus 3 term, and we're left with this equation here. And now you may look at this and think, well, this doesn't help us much because now we have one equation and we have two unknowns a and b with one equation, so we're still kind of stuck. Well, it turns out there's a couple different ways you can actually separate this into two equations. The first method we'll go over, you start off with that same equation, and now we can distribute those a and the b terms. And our next step is to just factor out the x. on the right. The x is kind of already factored on the left, but let's factor the x out on the right and separate this into, so now we have an x terms, or you have x times a plus 2b, and then we have the non-x coefficients b minus 3a on the right. So we've kind of separated this out into two different forms. And now, since we have an x terms on the left and right of the equation, and we have the non-x coefficients on the left and right of the equation, now we can just actually set those two different components equal to each other, because we know the x terms on the left have to equal the x terms on the right. So we can say 9x, if we neglect these two for a minute, we can just say 9x has to equal x times a plus 2b, because the x terms have to equal each other. And now we can divide by x, and we're just left with 9 equals a plus 2b. So this is one equation that we can get out of that initial equation. It's sort of a sub-equation we can pull out. And we're taking that same equation above, and this time we're just going to neglect the x term and set the non-x coefficients equal to each other. So if we neglect those, we're just going to focus on making those non-x coefficients equal, and we have 1 equals negative 3a plus b. So now we have two equations, two unknowns, and the algebra becomes more standard at this point. So we take this first equation here, 9 equals a plus 2b, and we just solve it for a. And now we can plug that back in to our second equation and solve for b. So you see we plug the a in here, and now we're just going to solve for b. So we just multiply that negative 3, distribute that negative 3 into the middle, and we get this equation here. And now we can solve for b. 7b equals 28, or b equals 28 over 7 equals 4. Now we can sub that back in to that top equation, sub in our b value, and we can solve for a equals 9 minus 2b equals 9 minus 8 equals 1. So now we've solved for b and we solved for a, and remember what we were doing here is we were trying to find the a and b values that make that initial equality whole, and it looks like we found those values. So now we can go back to our equation. First we have our a equals 1, b equals 4 we just found, and we had our initial integral we were trying to solve, and we decided that we were going to set this function here, this rational function, equal to the function a over 2x plus 1 plus b over x minus 3. And now here we've just added the integral, because if you integrate both sides, that equality still holds. But now we've already solved for a and b, so we can go ahead and plug those in. So we can say that this integral is equal to the integral of 1 over 2x plus 1 plus 4 over x minus 3. Now we can separate that integral out into two components using the basic rules of integration. And now we have two different integrals that we can solve using almost basic rules. I mean, we still technically need to use u substitution in this case, so we'll go ahead and do that. On the left side, we'll say u equals 2x plus 1. Our du dx is 2, so we can solve for our dx, and we can plug that back in, and we get the integral of 1 over u times du over 2. And now, finally, at this point, we have something we can solve, because we know this goes back to a basic integral, where the integral of 1 over u du is just going to be the natural log of the absolute value of u. Of course, we've got that half term out front too. And on the right-hand side, it's even easier. We'll call that v, use a v substitution here, equals x minus 3, and dv dx is just 1. So you really don't need to use u substitution in this case, but if you notice that dv dx is 1, then the u substitution doesn't have much effect, but just to be completely clear, we can use it. And on the right side, we just have 4 over v dv. And again, this is an integral that we can easily solve. So final step here is just to apply our basic integration rules, and we get this is equal to 1/2 the natural log of absolute value of 2x plus 1 plus 4 natural log of x, absolute value of x minus 3. So you can see the basic strategy here was we took a complicated rational function, we broke it down into two different functions that we could easily solve for, and then we applied our basic integration rules after, of course, applying a simple u substitution. So this is how you use partial fractions. There is another method that is actually, I think, a little bit easier to get your a and b values. So let me just show that. So for method 2, we start off with the same equation that we started off last time, where we have 9x plus 1 equals a times x minus 3 plus b times 2x plus 1. Now this equality is valid for all x. And since it's valid for all x, we're free to arbitrarily pick an x, and we can still trust that this equality holds. And if we're free to arbitrarily pick an x, how about we pick an x that helps us out a little bit? So imagine we pick x equals 3. And as you might see, if we plug this in, we'll actually be left with one equation and one unknown, which will be b. So when x equals 3, we'll just go ahead and plug that in for x. You see that that a term cancels out because we have a times 3 minus 3, which is 0. So this actually just simplifies down to 28 equals 7b, or b equals 4. And then we got to essentially do a similar thing to solve for the a value. So we take that same equation, and this time we set x equal to negative 1/2, so that the b term on the right is multiplied by 0, and it goes away, and we're just left with the a term. So we'll go ahead and plug in x equals negative 1/2. We plug that in here, and you can see that term on the right is going to go to 0 because we'll have negative 1 plus 1, and the b term will go away, and we'll be left with negative 3.5 equals negative 3.5a, or a equals 1. So comparatively, I kind of like this method because it seems like, for me, it takes a little bit less number of steps. But whatever method you like, feel free to use it. And this is method 2 for using partial fractions to integrate.